Hello there, this is our project for CS5335, where we are trying to create a search using line following to find a sound source. This group is Nolan Bock, Connor Frazier, Matthew Pashkowsky, myself, and Andrew Wirth. The goal was to create a control program for a robot to locate a sound source that would navigate along a series of lines. We had to build a gazebo simulation of a physical robot environment so we could do testing, and then we had to use the make block mbot ranger to test this in a real world setting. The work required was to write a custom firmware for the mbot ranger robot, which required creating a serial communication library, which was uploaded to Piazza. We had to build a gazebo simulation of the environment and robot, which required designing plugins to represent the mbot ranger sensors. And then once we had all that set up, we could implement a line following algorithm and a sound mapping algorithm.
So we knew some difficulties coming in. The physical robot didn't have an XY pose data like we had in Sim, so we were either going to have to create that or work around it. We were going to have to control the ranger from a different computer. This was discussed in class, and we'll talk about this later. We had to simulate the sensors of the physical robot in Gazebo, and then we had to figure out how to map sound location. This was new to us. Turning at intersections due to limitations of the physical robot. We will touch on this later as well. And then the space limitations, we all worked remote on this project and didn't really have, a big, large space as we would at school. So these were some of the challenges we knew going in. We did face some unexpected challenges as well. We thought that there would be, documentation and people who had, worked on the mbot ranger before. This proved to be not the case. There was barely any documentation for truly programming the robot. There wasn't much for communicating with it. We did know of serial communication from class. We thought that we would be able to get Bluetooth communication working. This proved too difficult, and we moved on due to time constraints. Next were some of the physical challenges, detecting turns during line following. We thought going in there were a couple more sensors than there actually were. Gazebo, we had never seen an example of simulating things on the ground. This was something we had to work through in order to simulate line following. And then also the sound sensor was a very simple one that only included really the sound strength, no direction or any more complex readings from it. And then lastly, due to no Bluetooth, we had to figure out how to work with the robot being plugged in at all times during motion and an extreme amount of batteries being used and changing them out very frequently. So these are the high-level changes in our plan. We originally intended to use the line follow algorithm from an academic paper we found. Later on, we're going to go through the changes we made to this paper. We also ended up adding XY data to the robot. We came up with a simple dead reckoning strategy, and then also accounted for error in the heading angle in the physical robot. We removed walls from our original maze. We planned to have lines on the ground and eventually build up to using a sonar sensor to detect walls. We removed this in favor of a simple Manhattan style grid. You'll see pictures of that in a little bit. And then, as I mentioned, we removed Bluetooth from the design in favor of serial communication over the wire. So this is a list of the interesting components. We built a custom firmware for the mbot ranger and then built a serial communication protocol using, command verbs and arguments. We'll see a deeper look at that in a second. We also created a development environment that would allow us to use, a single control program for both the simulation and the physical to avoid, mistakes in accounting for specific variables and other situations in, specific to either the sim or the physical. The next two, we had to create plugins in Gazebo to simulate sound and line following. These were both, original creations. And then lastly, dealing with trying to simulate physical sound data versus just constant numbers, which would have been an easier approach in sim. So here, the Ranger robot came with a firmware written by its creator, Bock. This was really unusable for our situation. So we created essentially a command argument protocol using space separated lists. And we wrote a custom firmware to handle those commands, basically a command parser over the serial that would take in commands from an external computer and either return data upon sensor read requests or execute action commands like move the motors. And then on the next slide, so here we created a library, a C++ library for the entire class to use. This basically abstracted the protocol that we came up with into simple methods. It handled creating the serial connection, reading data from the robot, and writing data to it or sending commands. This proved very useful. I think a lot of the class used it. This allowed us to basically just call simple methods like tank drive and give a few values, or read sounds, and this proved to make development much easier. Lastly, we used Professor Tuck's lecture demo of creating basically two robot classes that would work with the same brain. This included adaptations for differences between the sim and the physical robot, things like the values from the line sensor to differences in values used for controlling the motors and things like that.
Another interesting thing we got to work with was just the simulator in general. So we use Gazebo and a slightly amended TankBot, and here we see some of the maps we were working with. The idea behind what we were trying to do was to get a map that we could reasonably simulate the physical world, with the black lines being tape, and the intersections are kind of the white junctions where the tape meets but doesn't touch. So these are a few iterations of our tape, and now moving to the plugins. On the right side, you can see our TankBot with all of its plugins. The sound plugin is actually in the bot, so it rests like in the very middle, and you can't see it at all. But the camera plugin is the red strip on the bottom that has kind of like the downward cone. That's able to sense if there's a line on the left, if there's a line on the right, and then do some communication within the plugin to see, okay, if there's lines on both the left and right, that means we're on a line. And then we also have the distance sensor, but we didn't end up using that. So if you play the video real quick, we'll see our line sensors. Right now we're in line state 3, and our sound is 27. There we were line state 0, which means that we're not on a line. 3 means we're both sides are on a line. And here we're going to see the sound increase as we get to this intersection, and the sound source is kind of like off to the left at the end of that long line. And then it will decrease as we get up a little further. So if we skip ahead a little bit in the video, we can see even a little more. We can see the sound is now decreased to 17 because we got further away. Now we lost the line. We're going to decide to turn around. And what's interesting about this is that you'll see the line state go to 1, which means that just the left side of the sensor has a line on it, like right there, and then switching between 1 and 3 as it's kind of finding how it wants to orient itself. All right, and then on the next slide, we have a little bit more about simulating some of the controls and some of the different programs we use. So this first video demonstrates you making decisions on every single callback. So every time the robot updates, you see the cout is the information it gets. It basically decides where to go. The line states are the same, the sound sources and how we measure them are the same. But our basic strategy doesn't involve X and Y. It's just as we approach a intersection, we determine if we're kind of like facing up. And if we are, we go forward. If we're facing down, we go to the right. And if we're coming from the right, then we go to the left. And this is just basically our way of working around that we don't really have good X and Y data outside of the sim. So we can skip pretty far forward here and kind of see, yeah, so now we skipped past the intersection, that's fine. And we're just gonna kind of go to the end of this intersection, decide to turn around and go to the sound source. So at that point, we'll have come from the bottom, go all the way to past the sound source, turned around, gone right, turned around, and gone back to the sound source. So it's starting its turn again here, and it's actually gonna move the tape and interact with it in an interesting way that I'll talk a little bit more on the next slide. But so if we just skip forward a little bit, we'll see that this strategy was able to find the sound source at an intersection pretty well, but it has to explore all sides first because it doesn't, in like the worst case scenario, it could be in the last place it looks. So in this next video, we have a slightly different plan. Basically, whenever the robot's on a line, it just goes straight and continues on the line. But every time it gets to an intersection, it checks what the line was or what the sound was at the last intersection and tries to make a decision about where to go. So that's what you see in the updated last and updated current, the last two lines of the terminal output. Those numbers represent, the first number is the sound going up, the second is sound going down, third sound going left, fourth sound going right. And they can either be -1, 0, or 1. So -1 means the sound decreases if we go in that direction, 1 means the sound increases if we go in that direction, and 0 means we don't know anything about the sound or that it doesn't change at all. So as we get to this top, we know that we've passed the sound source. So updated current means that if the first instance is -1, which means if we go up, the sound will decrease. Well, we know that because we just came in that direction and the sound is decreasing. The second number means that if we go down, the sound will increase. We know that because we were just at the intersection below it and the sound was higher. And then the other two we don't know anything about. So we decide to go forward. The benefit of this is that you can make decisions quicker. So as we arrive at this last intersection, we'll actually know deterministically that we should go to the left. But the problem with it and why we didn't really explore it anymore is because it relies on X and Y data in the physical robot, which is not as good as in the sim. All right, and then moving on finally to the slide. So the next tough thing was tape in the simulator. So one thing we really didn't envision was that the reason you can easily interact with tape on the ground in the real world is because the adhesive sticks it to the ground plane, but there's no mechanism for that in Gazebo. So if we play the first video, you can see the bot is trying to turn around here. And as we, oops, sorry, I think that went back actually, you gotta go, it's way further. It's like starts at, yeah. So now we've turned around and gone past the tape, but basically the tape got dragged from being level to like this. And if we go to the next video, we'll see the other interaction. So here, again, the tape has been kind of pulled off by the treads. And now the second interaction is that the treads are interacting with the tape, pushing it below the ground plane. So you can see that by like the tape disappearing behind the bot. And if we were to turn around, the camera actually wouldn't see that because all it would see below it is white. So that was one major limitation we had in the sim and one thing we had to kind of code around. Heads up, I think you got to unmute, Andrew.
Thanks, Connor, or Nolan. Bringing it all together, the Gazebo plugins were added to the sim. The Ranger robot class used a serial communication library. We had 2 robot classes, but those 2 robot classes were controlled and being used by one brain program. And ultimately that one brain program had one set of algorithms in it that created 2 separate executable files, one for the physical robot and one for the Gazebo simulator, so that we were always working on it at the same time. The output in the physical world in the physical world, we ended up using different maps for our testing because we were working in different locations and restricted to home. These three on the right are a few of the maps that we did. That proved challenging because it made it a little bit more difficult to collaborate than we could if we were in the same room and all testing on the same exact map, but we try to do our best to make it very similar. And the process of building maps actually in and of itself is a challenge. As you can see from the left, this is kind of where we started, where we were just testing sensors and how well the physical robot actually picks up the different lines, what works best for it in terms of like moving forward. And we slowly built from there until we got to this maze like grid. And this is the result. We've actually had much better results. This is the best result that we've caught on camera. It proved to be challenging because for a lot of reasons. One of being if you set a camera in the middle of the room and then have to move the cord around it, you end up blocking the robot. Just a few other things where we just weren't recording at the right times, but ooh, here we go. So this robot, and we can hear the sound. So it's playing some music in the left corner. And it gets to the first intersection, and it's noticed that the volume has reduced as it passed the sound. So it's going to turn around there. So go to the next intersection where the volume has increased again. And it's going to make, because it knows that it turned around, it's going to make a discrete right or left turn, depending on which side you're looking from, and eventually find the sound. We thought that this was a good use case because it not only was something that we could, replicate in the bot world, but also something that maybe in the future could help in real life. Like say in situations where someone gets lost in a cave or a building collapses, you could potentially use paths and sound to find, survivors, or, there's some kind of real life application to it. For our academic papers, we use kind of a combination of 3 papers. We really focused on the first one, which was the auditory occupancy grid with a mobile robot. And this is how we kind of determine heuristics for robots at intersections and different locations of the robot. It's really challenging to use their exact algorithm because they have an array of microphones, and their array of microphones were directional. So they could tell which angle the sound was coming from and use that to triangulate distances, which we didn't have the opportunity to do. We had to drive to different places, check the sound there, and then move on. The next one is the algorithm for line follower. We actually were with a minimum number of sensors, we're pretty excited about this one because even though it proved to be challenging because this paper had 4 sensors and we only had 2 sensors, we felt that that was a bit of a win because it's with a minimum number of sensors. And we use this kind of as inspiration as we created our line follow algorithms and coding. And lastly, exploring light brightness and the inverse square law. The inverse square law not only applies to light, but it also applies to sound. And we use it as a guide for how sound behaves when doing our project in both the sim and physical world. Thank you. If you have any questions, please post them and we'd be happy to answer.